Hello everyone, welcome to fifth day of our linear algebra 101. So today we are going to see the geometric representation of the dot product. So as you can see in our whiteboard, we have three pairs of coordinate here. So I'm going to plot and we are going to analyze together what happens after plotting them. So our first vector is 6 by 2. So I'll plot this one at first. So 6, 1, 6 by 2. It would something be like here. So let's draw a line. It's not perfect. So this one is the 6 comma 2. Let's take the another one 2 comma 4. So the 2 comma 4 would be like here. And the another one is same. In the pair 2 we can say 6 to repeat it. So we will do the second one. So minus 1 3. So minus 1 3 would be something like here. I'm trying to be as much precise. So now minus 4 1. So minus 4 and 1. Sorry for slow drawing. Now that we can see that we have draw the all of the three pairs. Now let's do analysis. So among the pairs 6 and 2, we can see that there is a projection on 2 comma 4. Let's give it a name. Let's say it is A, B, C, D. So we can see that there is a small projection of B on A. And similarly for the coordinate minus 1 and 3, which is similar like right angle projection. And for the third pair, the minus 4 and the 6 pair, 6 comma 2 pair is kind of the extended. If we extend this line, kind of in the negative. So if I were to do a um, analysis of based on its position, if I performed or think them as a matrix, so let's say uh, 6 6 comma 2 6 comma 2 and 2 comma 4, it is meeting our requirement for the matrix multiplication. So if we multiply this one 6 into 2, 2 into 2 is something 12 12 to, and it would something result in the value 20. And similarly, if we do the matrix multiplication, 6 comma, sorry, not comma, 6 to minus 1, so we can already guess it would be something like negative, because here is negative 1. But if you focus on the angle here, and the angle between them, which is right angle, so we can take a short uh, cut here and directly write 0, because of the angle between them is right angle. And moving on to the third one, so if I perform this multiplication, it would be like 6 minus 24 plus 6, that it would result something like minus 22. I think so. Correct me if I am wrong, if my calculation is wrong. Now that we can see that from this matrix multiplication, we can see that when we multiply the first vector here, vector pair here, we are getting 20 here in the matrix multiplication. And one more thing to notice here is that the projection of A on B is on the positive side, and our result is also on the positive side. And moreover, we can see that the angle is 90-degree here between A and C, and it is resulting in 0. So, and it is kind of nearby the the origin. And on the third pair of the vector, we can see that we had to extend this 6 comma 2 vector and write the projection here like this. So it is giving the projection on the negative side. So for that reason, we are getting the negative value. So what message we are getting from this certain value and visualization? So if our value is kind of greater than 0, or the dot product of the two vector is greater than 0, the value always will be uh, on the positive side, like this side. It would hardly get on the negative side or below. So if we are dealing with something, it results in um, negative, the value would something be under this range. So if any of the projection is under, falls under this reason, we'll get a negative dot product, and the negative dot product is giving it as an idea that our value must reside on this side of the axis. And this middle line here is acting as an axis for the value dot product, which results in 0 when it is the angle is 90-degree. So now that we know some knowledge of bits, now let's move on to something a bit different, that we are going to see how we can multiply a matrix by a vector. So now we are going to see another example to ration up our concept. So let's say I have three equation, for example, a plus b plus c equal to certain value, then a plus 2b plus c equal to 20, then 3a plus 2b plus 2c equal to 70. So now that we have equation with, we can also visualize it in another way. I'm not going to go there, but we can break down these three equation into something that we can remember one of the things that we have learned in previously. So let's convert this system of equation or the linear equation into something else. So let's assume that we have two vectors with the coefficient of this equation and with the unknown. So the equation would something look like 1 1. I mean the matrix format of the vector, and this one would be like A B C, then the resulting value would be 15. So we are basically converting this into a matrix form so that we can later on sum up to another concept. So similarly, I'm going to break it down into this form. So 1 2 1. So if you can observe, if we do the basic matrix multiplication here, we would simply get this equation back again. So I am just breaking it down. Sorry, my arrow is missing. So this one is basically the breakdown form of the dot product. So now let's see for the remaining one, A, B, C equal to 20, 3, 2, 2, and A, B, C, and 17. Now let's take a glance at these three systems. So we can see the common vector among them is ABC. So how can we solve this and how can we simplify this system? So let's do a thing. Let's take the common part here and write it like this. So if I were to take common, so it would something look like 1 1, then 1 2 1, 3 2 2, or we could simply write it as, let's simply write it as a one matrix. Let's not make it three. Let's simply write it like this. So we can familiarize us with this the augmented value of the matrix that we did previously for Gaussian elimination. So we can write the product here like 15, 20, 17. So if we do the multiplication operation here, we would simply get the systems of linear equation back again. So if I multiply the matrix operation, multiplication, we will simply get this equation. So let's copy, paste for the sake of understanding. Oh, don't know what I did, but so we can simply, if we multiply this, we would eventually get this equation. So if even if we take the vector from here, we would simply return back to our basic linear equation system. So now what we are going to do, so if we want to perform this, uh, the, we have to be very careful that the length of this ABC matrix should be equal to the column length of here. So here we have three columns, and here we have length of the vector. Here this is our vector, so the length of the vector is 3 here. So if we had something like less than the value or more than the value, it would not work. So we have to be very mindful of that. But in case we have added an additional row, sorry, in case we added an additional row here, the value would, here is not changing because it would simply result another row here in the product or the value here. We would simply get another equation because the number of column is still 3, but there are 4 rows here. So this was the basic understanding of the dot product and the matrix multiplication. So we can basically getting the uh, we're going back to our roots in the previous session. So now that we are done with some theoretical concept, we are going to see some code, short code. So let me change the window. So now, as we have learned how we can use the numpy, so we are going to use the numpy to do the multiplication. So we are importing the numpy. Now, as you can see, I'm using Python and passing the array here and multiplying it by now multiplying is 3 by 3 matrix, and this one the example B is 3 by 2 matrix. So I'm initializing their value. Now we can perform the matrix multiplication with the built-in function of the numpy matmul, which is the short form of matrix multiplication. So if we simply run it, we would get our value, which is very fast. If we were to do in hand or manually, it would take some time. So you can also use this form, or you can simply use the at the rate form to do the basic multiplication. But you have to keep in mind, you must the follow the rules of the matrix multiplication. So we must, the first matrix and the second matrix, column and row should be equal. So if I have 3 by 3 and 3 by 2, so its row and column should be the equal for the first row's column and the second row's second matrix row. So now that we recall that, now let's see a different thing. So let's see what happens when we run this code. So we are saying that something, it is saying that input operand 1 has a mismatch and its score dimension 0. So what it is saying, we can see that if we do, if we remember previously, we can see that, let wait a minute, back to the board. So we remember that if we multiply two vectors of 3 by 3 or 2 by 2, we would simply get the same result regardless of the order that we multiply. So if we multiply A by B first or B by A first, we would simply get the same result. But here we can see that the order is not same here. They are not of same order. They are 3 by 3 and 3 by 2. Their dimension is not same. So it is resulting in an error. So it is giving us an error. So now that we can also do this multiplication through the at the rate method, it will simply say the same. Now